My name is Sergei. I'm working as a quant, and today this talk will be a bit less about programming and a bit more conceptual, a bit more theoretical, maybe. So what I'm going to tell about is another approach to setting up large-scale computations that proved quite efficient in many situations, and it allows you to build systems that can do, let's say, minimal amount of overhead work when some small changes have to be applied to it. So, um, so let's start from some basic math definitions. Probably, as some of you remember, what is a graph? A graph is just a set of nodes, some of which are connected with edges, some of which are not. So let's say that V is a set of vertices or nodes, as we will call them, E is a set of edges, and a graph can be either directed or undirected. And the difference is whether we care about the order in which nodes are being connected or not. So today in our talk, we will be always caring about it. So all our graphs will be directed graphs, which means that it's like two-element subset of the set of nodes is ordered one instead of being unordered. And all of us have some intuitive understanding of what a graph is or what it can represent as a model. So I have some small picture that I will use later as well. So yeah, that's how we usually draw them. So nodes are just some circles and edges are arrows that connect them. And given that arrows are like actual arrows, this means that there is direction defined on that graph. So what is a computation graph now? Basically, not very different from a graph. It's a graph when each node represents a computation and edges reflect dependencies. Dependencies, let's imagine some very simple function. We need to compute x multiplied by y plus z. So here is the graph from the previous slide, which demonstrates how this function could be computed. So raw inputs are basically nodes, and operations are nodes as well. So x multiplied by y, that node represents basically multiplication, and it accepts two raw inputs, x and y, and f represents addition, plus sign. You can imagine it instead of the letter f, and it sums together x multiplied by y plus z. So that's how we could in code represent that function. And I will talk later a bit more about how that kind of code could look like. But first, let's consider a couple of examples. Well, it's better to avoid loops, but sometimes loops are possible if there is some contingent conditions. But yeah, usually it has to be connected and it has to be acyclic, which means that it's basically a tree. Yep. So to make things a bit more intuitive and to prove that all of you have already dealt with some systems that have some graphs underneath them, here is a simple example of an Excel spreadsheet. So if some of you remember, when you type something and you change one cell, you don't have your whole workbook recomputed. You don't wait for a lot of time, just cells that depend on what you updated, only they are recomputed, and everything else is untouched, which means that an Excel spreadsheet somehow knows like how things depend on each other, and it does so by utilizing a graph underneath. Another simple example is a neural network, artificial neural network. So here, the most popular frameworks for building neural networks, at least in Python, are PyTorch and TensorFlow. And they basically allow you to define this kind of graphs, where input layer is basically the representation of your input object, like some features. Each node represents some feature. Some hidden layers are basically, so each edge represents a dependency, and hidden layer is some activation function applied on top of some linear combination of features. You have multiple of them. Then in the end, you have an output layer, which also somehow linearly aggregates the previous outputs from the previous layer and applies a nonlinear activation function. And yeah, that's a pure graph. So that structure is what allows us to compute things efficiently and to do a backpropagation algorithm that allows us to learn actual weights that optimize some relationship between input and output. So why actually it's important? All these things I have already mentioned a bit, but let's look at them a bit closer. So what are the benefits of it? What are the reasons why we should somehow prefer to use graphs for setting up our computations? So let's imagine that in some session, we have already computed f function once, and we have it computed for some inputs x0, y0, z0 from one of the previous slides. And this thing, the data structure that represents our graph, has all those values already cached on top of the nodes. And let's say that we want to compute f again, but we need to change only z. So what do we need to do? The very simple, like monolithic implementation, I mean, you can all imagine a simple implementation in any programming language of function f would recompute x multiplied by y. But if we set up computations like that, that will allow us to avoid that and to recompute only some. And to do that, we need an algorithm that will, first of all, determine that z node has been changed, and will traverse the graph to mark all nodes that go after it, that are upstream relative to the z node, as, let's say, dirty. That's the terminology you can use, which means that their values cannot be used. The values that are stored are wrong. So that before we recomputed f, that node still stores f0, but z was updated, which means that f has to be marked as dirty. To do that, we can use simple graph traversal algorithms. And the value that we are interested in will be only recomputed when it is requested, which is also an important property. Number two. So apart from the fact that we avoided completely doing this multiplication that we don't need, we also have this concept of lazy evaluation that is allowed by setting up your computations through a graph, so that f is not recomputed immediately when the z is updated on graph. F will be computed only when it is requested. And how it works, another graph traversal algorithm picks up only dirty nodes underneath, and recomputes only their values based on the updates or some other um, changes that were made potentially, but does not recompute what has already been computed at least once and can be readily used from the uh, cached state of nodes. And another, probably this is like the most important thing, at least in finance industry, that setting up your calculations through graphs allows you to do so-called dependency tracing, which can be important in both directions actually. So more frequently it is important like downstream, where you discover what are the dependencies of some quantity of interest of a certain type. So let's say that you compute some function f. Of course, it's very complex. I mean, it can be very complex. Yeah, I'm using some simple examples, but you can imagine a really hard to compute quantity that can be, let's say, some portfolio of financial instruments or some complex simulation. And you want to find out what are the things that you are exposed to, like what are your actual dependencies. In terms of finance industry, this will be like your market exposure, for example, like what are your things that you need to take a look at when you compute sensitivity to different variables. And yeah, you can, of course, when you do those graph traversal algorithms, you are usually interested in dependencies of a certain type, which means that you can also filter out whatever you are really trying to look at the moment. But it is also sometimes useful like upstream, where that means that wherever you change some input, if you have your like complex computation set up as a graph, you can see what is going to be affected, what are the actual nodes upstream that will be changed. And again, sometimes you are more interested in nodes on only given type. And yeah, let's consider some example. So there is at least one framework, but of course there are lots of them. And this is just a way to show you how that that can work. So let's say we have some like basic functions as well. This is like a toy example. And we want to compute some like total for some data, for some set of data. This is how, using this framework, you can define that computation. So basically, you instead of performing it, you are building. That can also be written using decorators, but here it is like a more simple, more simple way to define it. You are building some graph that you will later evaluate. So let's say that you want to compute some total of some function applied to some stream of data. And that's how that will look like in your system underneath. That will be some graph. There are some libraries allow visualization tools, some are not so user friendly, but anyway, that's what they do. They build these kind of structures, computational structures, and then you can, of course, evaluate it. So yeah, let's maybe talk a bit about other benefits as well. So one of them is that graph actually setting up computations like that encourages you to design your code better, because that design will be later the thing that you will be able to trace, to override. And in that case, it's usually more maintainable, and it's easier to extend, it's easier to change how you perform your computations, to plug in some additional logic. So to visualize this idea, I put like the screenshot on this slide that shows that we were basically forced to define all these functions, all these basic functions, to actually make it work, to build this kind of structure. And the second benefit of setting up your computations using graphs is usually that it allows you to execute some parts of your computation concurrently. Because again, based on that system, based on that picture, you can see that you basically get parallel execution for free. If you would write here just a loop as it is, I mean, without task delay, just like increase X, double, then add, increase, then double, then it's like it computes things linearly. But given that here it doesn't compute anything, it just builds this structure. When you actually evaluate, if you like write your own framework, you have to make it efficient. But the frameworks that exist, that already exist, they usually find out what are the pieces that can be evaluated simultaneously, and if your hardware allows that, they will be evaluated simultaneously. And the final part of what I was going to tell is some applications where it's actually crucial. So I already provided some financial applications where we are very frequently interested in what are the market factors that we are exposed to. And setting up computations as a graph allows to do this basically more or less automatically. That allows you to do different simulations and so-called like scenario analytics. It's when you can tweak different inputs of your calculation and see what are the sensitivities to those inputs, which is like an analytical task performed quite frequently in each and every industry probably. But apart this like third point about simulations and scenario analytics, the other usage where this is quite crucial is whenever you have systems that are reactive, that have to react to some online changes. So to some real-time updates, if it's like some kind of dashboard, some computation that is performed underneath a dashboard, or whenever it's some UI, as mentioned also on the slide, when the components that are affected have to be re-rendered, updated, instead of the whole system, like in Excel spreadsheet that we mentioned at the beginning. Thank you for the question.